and CEO of the New Mexico Technology Council. And we're thrilled today to have Matt Fetro from AFRL, Air Force Research Lab, talking with us and giving us a virtual tour of AFRL. We've done this for a number of years, but in person. And so we had limited numbers, had to deal with that, getting everyone on base. So we're thrilled to have this opportunity. Thank you so much, Matt. I think most of you are familiar with us, but if you're new, welcome. And we're so glad you could come and participate today. The New Mexico Technology Council is a statewide member-led organization committed to supporting the state's vibrant tech ecosystem. We do that through networking, professional development, public policy advocacy, and workforce development programs. We always want to promote and support our members, and I think the really important thing that we provide is that those introductions and the ability to network with your peers and get to know people in similar fields and or with similar interest areas. We do this through our monthly peer groups, big data and AI, cybersecurity, women in technology and 3D printing. We have 2 annual signature events. Women in Technology, our awards, and of which we've now recognized over 100 women in 13 years, and our Experience IT conference. I also mentioned public policy, member promotion, and features. And we can go to the next one, Emily. And by the way, I'm very thrilled to have on the call, Emily Bennett is our marketing and events manager with the New Mexico Technology Council. Mary Tiemann is our membership director, who most of you have had the opportunity to meet. And so I'm just really honored and privileged to have such a great team to work with. So we always want to recognize our community partners, thank them for their support of our organization. We couldn't do this without them. As you can see, many really diverse industry representation. And so we're thrilled to have such a great representation of companies as our community partners, and as well as our membership. We really appreciate our support of our membership. So we have a number of upcoming events. Our Women in Technology Happy Hour will be next week on Thursday, the 26th. We're going to be watching LFG and discuss equal pay, Women in 3D Printing, Roadrunner 3D and Westwind, which is a program that Sarah leads from Fab Lab Hub and New Color Network. Our next cybersecurity meeting, September 9th. And then in October, we'll be having our next big data and AI peer group meeting. And you can see back at the bottom of that slide, but you can actually always just go to our website and see what our events we're having and sign up for them there. Also, we're asking you to save that date. Our Experience IT conference is back, and we're going to be having it on Thursday, November 4th. We're planning it now to be at the Embassy Suites in Albuquerque with a basically hybrid with virtual as well. So we want to thank our Experience IT sponsors that are already all jumping on board and providing their support for this event. So if you're interested, you can reach out to Mary Tiemann, and it's also on our website. So join our mailing list if you're not on our mailing list to see these kind of events that we're having and to hear about activities in our that we're holding, as well as getting to know other companies and hearing about our member promotions. And also, please follow us at NMTC on social media. So you can go to our website to join the mailing list. Actually, Emily will also put our the mailing list link in the chat. Okay, and with that, I'm thrilled again to introduce Matt Fetro with AFRL, the Technology Outreach Lead. And Matt, I will let you talk a little bit about, as you get started, what you wonderful, all the amazing things that you all are doing in your outreach programs at AFRL as well. So take it away, Matt.
Thanks, Deborah, and thanks so much for having me today, and thanks, folks, for joining in on this virtual format. Again, I'm the Tech Outreach Lead for AFRL. I've spent a long time working for AFRL. I won't say how long, mostly as a program manager building optical systems for satellites. But the last few years, I've transitioned to really working our STEM outreach programs, our economic development programs, and our tech transfer programs. Don't tell anyone at AFRL, it's a lot more fun to do this because I actually get to interact with all of you and just diverse groups of people and try to make the state better. So, again, really pleased to do this. As Deborah also said, many years we've been able to have a few folks, a van or two full of folks come on base. We like to think of AFRL as being very open on base to show our laboratories off and whatnot. We're not as open as I'd like to be because it's actually kind of a pain to be on the base, but we've been doing that for years. This year it's just not possible or practical to do that, and so we've pivoted to a bunch of different virtual guided tours, I call them. And so we've been giving these tours for lots of different folks, school groups, ROTC groups from around the country. And it's been kind of interesting because while the format isn't really as cool as being on the base in person, it does have some advantages. It's a lot easier for you guys and frankly for me, and we can get folks from around the country as well. And so, as I mentioned, in ROTC groups, one of my favorite tours we did was for about 75 ROTC cadets in the Air Force out of the state of New York. Right, as I joked with them, right, they got a little view of what we're doing here in the Air Force in New Mexico, and frankly, they're never going to come to visit us, right? They never could have come to visit us. So, if you're okay with this, what I'll do is I'll share my screen and go through some Google Earth and some videos I'll talk over and some slides to show you what we're doing on the base. And please, this is hard, I know, but ask questions as I go along. It's hard because of the format and because I tend not to shut up easily. But Emily, Deborah, please interrupt me because this is for you guys. I really want you to get a sense of what we're doing. And frankly, it's more fun, and I learned something if you interrupt me. So the other thing I joked about is I've discovered over time that while I kind of know how to run Zoom, I can't talk and switch screens very easily. So because I'm about to share my screen, which I'll do now. And then my other frustration was I have to ask if you're actually seeing something that says virtual guided tour of AFRL. And if I got that right, you are. Okay, thank you.
We are, absolutely. And if everyone would please mute yourself. If you're not muted, you can put questions in the chat and we'll share those with Matt as we go along.
I often think I need a lot more monitors to help do this, but then I remember that I couldn't probably see all of them at once anyway, nor have the skills to transition. So we'll start here with Google Earth. So many of you know about AFRL. I'll try to go through some of these just a little bit briefly. But I wanted to set a little bit of context of what AFRL, what the Air Force Research Lab is. So here in Google Earth, hey, look, the United States. Let me give you just a quick overview of our laboratory. Air Force Research Lab, what a wonderful name, AFRL sometimes it's called, right? Technology for the United States Air Force and now the Space Force. I think you're all probably aware that the Space Force is our 6th branch of the military. It's also a Netflix show. If you haven't checked that out, that's how I became familiar with the Space Force. And we're a laboratory that's distributed across the United States. So we think of ourselves as a single lab, but we really have 5 main operating locations. Our largest operating location is in Dayton, Ohio. That's also our headquarters. It's also the birthplace of aviation, if you believe their license plates. So that's kind of a big deal. But we also have locations in New York State, up in Rome Air Force Base, in Eglin Air Force Base, and here at Kirtland in New Mexico. Each of those locations has a technical specialty. So in New York, they work on information technologies mostly. The munitions guys are all, and gals are all at Eglin Air Force Base. And here at Kirtland, we work only on 2 things. We work on space technology and something called directed energy, which are lasers and microwave weapons. And that's what I wanted to talk and show you a little bit about are those 2 technologies. We've got about 2,000 people that work at AFRL. About half are government civilians like myself and military members. The other half are contractors that come to work at Kirtland every day. And of course, 2,000 is a fair-sized company, but for a national lab in New Mexico, that's pretty tiny. Los Alamos and Sandia both are in the 12,000 plus. So we're kind of a baby federal lab. It's also different in that, right, we only work on a couple of things, whereas those larger DOE labs work on many, many more diverse technologies. All right, I think that's all I wanted on this slide. So the good news about not being on the bus is I don't get car sick. So that's great. The bad news is sometimes these Google Earth images make me a little bit car sick as well. You all know about New Mexico and the great technologies that we work on across the state. When I'm talking to students, I usually point out things like where the spaceport is and other sorts of things, including our great research universities, right, that are all developing technology for the country. But I'll continue on to zoom in further to Albuquerque. You're all familiar here as well, right? It's sort of in the center of Mexico, although not quite, and it's of course at the crossroads of our two big interstates. That drawn box here is me tracing out where Kirtland Air Force Base is. And that's where AFRL's home is, right? We're at Kirtland, and it's physically a very, very large place. It's sort of startling, you know, New Mexico is a large physical state, but this is one of the bigger bases in the country. That drawn area is more square footage than Washington, D.C., for example. We're actually bigger than the District of Columbia. And that's great. It's also a really weird base in that it's got a lot of different, we call them tenants, a lot of different organizations sort of have their home on that base. Obviously, Sandia National Labs is on the base, AFRL, but there's about 100 other organizations, some big, some small. The base is also interesting that there's a lot of real estate to do things like testing of directed energy. There's a lot of physical space just to do lots of different kinds of things. And so it's a real asset to both, you know, New Mexico and the nation. Most of AFRL's operations, aside from some test facilities down the south end of the base, are kind of around the airport. You all probably realize the Air Force Base shares the runways with the Albuquerque National Sunport. That's pretty common. And we've got a lot of aircraft and whatnot in this region. Before jumping on the base, I wanted to go to two other stops quickly because we do have a growing off-base presence as well. So for example, we do a lot of work with the University of New Mexico, particularly the School of Engineering. And so this is in the south part of the campus. Well, I guess it's called South Campus at their Science and Technology Park. We have offices here at this building on the third floor. We also share, it's actually right here, a research laboratory with the School of Engineering. This particular laboratory, we won't go into this one much detail, works on advanced, you know, manufacturing. 3D printing, machine learning, a bunch of other technologies to try and figure out, frankly, how to get satellites to be manufactured in a more automated fashion. Currently, we kind of build satellites all by hand, and we'd like to do differently. And so that's just one example of some of the off-base research we do. One more example before we go back onto the base is we just opened up a new collaboration facility in Nob Hill in Albuquerque called Q Station. The background behind me is actually the interior of Q Station, although I'm not there now, I was there a couple hours ago. This is really a new collaboration facility to motivate collaborations between industry, academia, and the government to try and mature the space economy, both in New Mexico and around the nation, both space and directed energy. We'll be incubating companies in this location. We're having conversations and running programs out of here, really to figure out how do we, in New Mexico in particular, accelerate the pace of technology economy, both for our state and for the country. So we're really excited about this location. We've gotten a lot of positive feedback. So if you haven't been there, please come visit us, bug me, and help us, help us collaborate to make the state even better. All right, enough Q Station plug. If we were doing this in person, we would probably all go to the Truman Gate, and we would have all driven there separately, and we'd pile on a bus here, and we'd go right through the Truman Gate pass office. Ideally, I would flash them some credentials, and they'd pass us through. If they're having some exercise or something, we might get stuck at the gate. It might be a bit of a pain. So again, there's some advantage to doing this virtually. We're going to stop in two places. We're going to talk about directed energy first, particularly our laser labs. And I'll show you the inside of those labs. We'll talk a little bit about laser technology. And then we'll go to the space side of the house and talk a little bit about, in particular, our small sat work, our small satellite work, which is some of the most important and visible work we're doing in space research. Any questions yet? Anything I missed?
I don't think so. Anyone want to raise their hands, or anyone have any questions for Matt?
All right, over to directed energy. So directed energy is what it sounds like. We're directing either visible wavelength or infrared light or microwaves at something to actually affect that something. And so we want the lasers usually burn something, and with microwaves, we're usually trying to affect electronics. And so that's what we mean by directed energy, as opposed to lasers that are used for telecommunications, solar energy, those sorts of things. I don't particularly care for the phrasing, but no one will let me change it. So this is our main laser laboratory facility. And one thing you can notice right away is it's actually hooked to the support runway. That's actually a pad for aircraft, and we've got a very large aircraft hangar here. So you might be wondering, well, why a laser lab? Why is it by runways? And it's because we're the Air Force. So long before there was a Space Force, we worked mostly on airplanes. And one of the main goals of the Air Force for many years has been to put essentially weapons-capable lasers on airplanes. We've done this before, actually. Those of you who know the technology, the Air Force built and finished the airborne laser. Great name, ABL, airborne laser. And it was a chemical laser put into a 747. We finished that up 10 or 15 years ago. It was very successful, except for it was a chemical laser and it filled an entire 747. It's actually the stretch 747. It wouldn't fit on a regular one. Filled the whole thing. It was very effective. We actually shot down missiles with it in tests. But the problem was you had a chemical laser, which is a messy logistics problem. And you also had an aircraft that could do nothing but shoot down missiles. It had no other use. And so we've kind of gone away from that technology. And this roadmap shows you where we're headed today. We're only working on electric lasers. These are lasers that are solid state, we call them. You basically use electricity from a wall socket, or in this case, the aircraft. And we want to put these lasers on aircraft that have some other purpose, like fighting a real mission or carrying cargo. And so our entry-level capabilities on the left, where we would put kind of as an add-on, what I'll call a 10,000 watt laser, I'll get to that in a second, on an aircraft to defeat incoming missiles. This is a big problem in the Air Force, right? We're very effective at fighting, but if we go out into conflict, the enemy shoots missiles at us, we shoot missiles back. And again, we're very good at this, but at some point, it's kind of this medieval game of who has the most missiles. And so in the future, what we'd like to do is shoot down those incoming missiles just using laser energy. And so you've got a kind of entry-level capability, and then in the middle, you've got a more powerful laser on a stealth aircraft, right? Something that's a little more modern. And then eventually what we'd like to do is put a very high power laser on aircraft that, as they're being built, basically build in the laser to the aircraft rather than adding it on after the fact. You buy a car today, it's going to have air conditioning built in. In the old days, they used to add it, kind of at the dealership after the fact. And so we're hoping that future aircraft will technology actually build the laser weapon right into the platform.
Hey, Matt.
Mm-hmm.
So we got a couple questions. What is the percentage of basic versus applied research at the Kirtland AFRL?
Yeah, so the government breaks down research into research development and test and evaluation into like 7 bins. And we work on basic research, advanced, and applied. I think that's the direction, or applied and advanced, the first 3 levels. At any rate, about 10% of all it is basic research. Most of it is in that mid-level, which I call it 6.2, but it's, I think, applied research. And then advanced is the third category, we work on some, and that means you actually have a specific application in mind. The things I'm showing here would absolutely be that advanced research. But it's only about 10% of basic research.
Terrific. Sarah also has a question. Sarah Boisvert, we're working with Wright State University and Wright-Patterson Air Force Base on digital badge micro-certifications in photonics and laser material processing. Does AFRL and Albuquerque collaborate, share programs with other AFRLs?
Yeah, absolutely. Sometimes that's hard because of culture and distance, but it is only one AFRL. That didn't used to be the case 2 or 3 decades ago. They were all very separate labs. We have one boss, Major General Pringle now. She's out of date, of course, but yeah, we try and share and collaborate as best we can with all of the different locations.
Terrific. Thanks so much.
All right, one other quick slide, and then we'll get into the lab. I briefed that slide some years ago, and people are like, well, what's 10,000 watts? How big is that? Big or small? And just for reference, a common laser pointer might be on the order of 2 or 3 milliwatts, 0.002 watts. And, it's pretty safe. I've got one here now that I think about it. I should flash the camera. But it does have a warning label on it, and it can cause eye damage. So, that's the brightness of 2 milliwatts. If you go up 1,000 times in power, you can still get a handheld laser. There's a picture of one there. You can actually buy those on Amazon. They're very, very dangerous. They aren't approved for sale in this country. And a 2-watt laser is very dangerous. You can burn your hand. You could probably permanently damage your eye. You can light paper on fire. And we actually do that in some of our STEM demos. To go up another 1,000 times in power, now you're starting to get interesting from a high energy laser perspective, or a research grade high power laser. It's still not that powerful, but that fiber laser in the center there is what that ends up looking like. And I'll take you into that lab next. All right, in order to take you in the lab, I have to jump out of this to see if this keeps working. Deborah, do you see the fiber laser lab now? It doesn't sound like it.
The roadmaps, lasers on airplanes?
Nope, hang on. It's happened. See, I told you that after all this time, I still don't know how to share. Stopping sharing, you're going to reshare. It's finicky. All right, that's better. It should be.
Yep.
Very traditional optics lab. This is one of many we have. It's a fiber laser lab. A couple of the folks that work there. A couple things to point out, they're wearing goggles because this laser is very, very dangerous even for scattered light. But the funny thing is you wear laser goggles, then you can't actually see the beam to figure out what you're doing. And so he's got a device, the guy on the right, to actually see the beam. Again, one of many labs that are kind of cool to go into. The fiber lasers in the center. Let's go through this. Oh, this is in the way. I need a bigger screen. So a fiber laser is essentially using fiber optics as the amplifying mechanism to create all that light energy. So the fiber optic is not a lot different than telecommunications fiber you hear about all the time, right? Comcast uses it, everyone else. It's made up of different materials. It's doped differently. And then this very long fiber, it's typically hundreds of meters, is electrically charged so that the light gets amplified, through distance. And so we could have stretched this out and made it 100 meters, but the lab's not that big, our airplane's not that big. So what you see there is wound around a mandrel, and it's either casting some sort of blue or violet light. That's probably a better shot of it there. It's pumped with a set of laser diodes. And again, as the distance of the fiber increases, the light gets farther and farther down, it gets higher and higher power till it eventually comes out the end of the fiber. And that's what you see here. It's being coupled into a set of lenses, then get focused onto the target for this test. So it's about 2,000 watts of laser light that's inside that fiber. You can see something else here. In creating a high power laser is actually only one of 3 or 4 challenges in creating a laser weapon on an airplane. And another of the challenges you can kind of get a sense of here, all of these tubes and whatnot are water cooling in this case. If you've got a couple of thousand watts of light energy, these things are only 20 or 30% efficient. You have many times, 2 or 3 times more of that of heat, waste heat that are coming out of these things. It's not unlike waste heat out of an air conditioner. And so you've got to figure out a way to get all that heat off the laser. Otherwise, the laser will actually melt itself as it's lasing. And so we actually work on a lot of thermal technologies that would be appropriate for aircraft to make sure we can get the heat off the laser and out of the aircraft and maintain the operation. A few more pictures, then I'll show you what this looks like when it actually fires. I hope it will. So this is actually behind that laboratory, some of the cooling technologies. That's a friend of mine, Emil D'Atencio, one of our senior scientists working there. I mentioned about 1/3 of our federal employees are actually military members. These are typically military members that have technology degrees, often from the Air Force Academy. They're typically early in their career. We have a few senior militaries, but it's very common for technical Air Force members to come through the laboratory as one of their stops in their career. People get confused all the time. They think, since I work for the Air Force, I'm in the military. I'm not. I never have been. I remind them it's not unlike other federal employees, IRS agents, postmen, Air Force people. Same sort of deal. So I sometimes, particularly with the students, I joke about movies, right? And ask folks to put in the chat their favorite movie laser. For those of you of a certain age, my favorite is Real Genius from 1985. Lots of reasons I like that one. But movies have not done any service to the science community in terms of what does a laser look like and do. There are many things that are just flat wrong. First is my favorite is oftentimes you'll actually hear the laser, right? People even say pew pew and it makes a sound. Okay, it doesn't make a sound. Sometimes you can hear the equipment, maybe you can hear something exploding, but there is no sound. The other thing, and it's not all that intuitive, is you can't even see the laser beam unless something scatters the beam back into your eye, hopefully only a little bit of it, right? The laser is pointed at your eye. You're not going to see that because you're going to lose an eye. And in this case, this particular laser is going from left to right onto the target. And you can only see little pieces of it. And that's when smoke, dust, or something is in the beam, scattering that beam back to your eye. So you don't see this big giant beam coming out. That doesn't make any sense. And the third most frustrating part is that in the movies, when the laser beam hits something, usually that something explodes in a big fireball. Well, that doesn't happen, right? Unless there's a reason for the fireball to exist. Maybe it's filled with gasoline or something, right? It doesn't actually happen that way. The laser is just depositing an intense amount of heat, well, light that's converted to heat in a small spot. And so it's a lot closer to something like welding, which uses typically electricity to create that heat instead of light, than it is an explosion. And so I'll show you a couple of laser burns here. This is a very short clip to give you a sense of sort of what I mean by welding, and then a longer clip next. In this particular frame, the laser is going from left to right. It's just hitting a piece of metal. And all of those sparks you see, and I'll show you them moving here in a second, are just like welding. They're pieces of metal flying off from that intense small spot of heat. That's real time. It's not all that exciting. No booms, no explosions. So this last one I want to show you is a much longer clip, and it's a little complicated. If you were at our laser lab in person, one of the things we love to do is to commemorate the event with what we call a challenge coin. For those of you who are familiar with the military tradition, we've got these coins that commemorate our organization, things like that. I should have brought one with me. They're large, they're thick, they're typically kind of fancy and painted on both sides, thick metal. And so what we do is we burn a hole in it. And I'll show you what a coin burn looks like. If we were there in person, I'd give the coin to somebody. But it brings up a third point, because even with a very high power laser, you have to hold the laser beam on an object a fairly long amount of time for it to burn a hole through. It's not instantaneous in any sense at all. So here, let me go ahead and show you this. So the laser started, it's coming through that lens and being focused onto a spot on that coin. It's being held in one spot. All that smoke you see is from the paint. We're actually now burning the paint off of the coin, which is why when you weld, you typically take the paint off first. It's probably pretty toxic and nasty. So this is in real time. Now it's finally burnt through the paint and it's going into the metal layers and melting through those. Again, this is a couple thousand watts of laser power that's doing this. Not the biggest laser we'd like to put on an aircraft, but not something you'd want at your house. We'll let this go for just a second or two more. You can actually see there's now a fire on the backside from the paint catching on fire. And finally, it'll burn through the backside paint, and this will be over, and we'll have a coin burn. Now, these things are fairly thick. They're surprisingly, I don't know what it is, 3/8 maybe, 1/4 inch. And that's the backside finally being burnt through. So this brings up really the last point that's a real challenge for lasers. You've got three things: making the high power laser, that's hard; getting the heat out of the thing and keeping it from crushing itself is hard. And then the third thing is holding that laser beam on the point that you want to that you want to burn something up. It's easy in a laboratory. We have everything in a fixed mount. But if you're on an aircraft and you're shooting at some other moving object, it's very, very difficult to keep that beam on that missile, for example, for on the order of many seconds to actually burn a hole through that missile and defeat the missile. And so we've got a lot of technologies and a lot of control loops working on sensing, working on, again, computer algorithms to aim the beam, keep conditioning the beam and whatnot to actually to hit the missile at a fair distance. So those are all technologies we're working on. And I think that's the end of my laser shtick. Mentioned as well, we work on high power microwaves, but rather than going to that part of directed energy, I think we'll jump over to the space side of the house unless there's any questions. Yeah, we actually do have signs at the laser lab saying, do not look into the laser with remaining good eye. They're awesome. I'm going to reshare Google Earth so we can jump to space vehicle side of the house. So it's interesting, directed energy and space are both in Albuquerque for somewhat historical reasons, but also because of the large test areas, just the large amount of physical space that's in Kirtland Air Force Base. There really isn't that much overlap between the technologies or the work that's being done by those two. Accidentally in one of these virtual tours, got the audience to think that those two are tightly linked. We're not working on space lasers. And that's as much fun as that is in the movies. That's not a thing that's a big deal for us and whatnot. It's airplanes and lasers, and satellites, typically don't use high power lasers. But let's jump to the other side of the runway where all the space stuff happens. I want to talk to you about and show you the space small sat lab. But first, I want to talk about the 3 things we work on in space, because it shows you really the breadth of technologies that go into being good at space technologies. So the first is called our Battle Space Environment Laboratory. We have actually the leading group within the Department of Defense for understanding what's going on in space. So often we talk about space as being a vacuum or there's nothing up there. And when I talk to students about what's in space, they always think of space debris. And that's an increasingly difficult problem. But long before debris killed satellites, it was the sun that killed satellites. And so this is a new building for us over the last few years. So it's really focused on understanding small particles, energetic particles like protons, electrons, and whatnot that all came from the sun and get trapped in our magnetosphere and whatnot around the Earth. As our satellites go around and around, they pick up all those particles. And currently, and hopefully forever, it's those particles that end up limiting the life of our satellites. Usually not so much space debris, at least today. So this is a group that does that. They've got a lot of cool chemistry labs in there. A lot of the basic research we talked about earlier, that 10% comes from this group, because understanding the sun, understanding all those particles is really, really fundamental work. The second thing we do, second big category, is we make parts for satellites. This is our components laboratory. These guys describe it a lot more fancy, but it's essentially making satellite components either cheaper, better, or smaller in many cases. So they work on solar cells, thermal control systems, navigation systems, sort of all the things you want in big or small satellites. These guys have actually done a really good job. There are highest number of patents. A lot of the technologies that come out of this group can actually be used in other sorts of things, automotive applications, you name it. The third big group we have actually flies satellites. We build and fly satellites, and that's what I wanted to show you on the space vehicle side of the house. We don't make the satellites that the Air Force uses operationally. We only make test satellites, and I'll show you that. But the kinds of things we learn in our test satellites actually sometimes get into the future systems that the Air Force then buys from whoever they want to buy them from. As kind of a setup for this, I wanted to show you one chart just to provide a little bit of context on space. Many of you know this. Some of you probably know this a lot better than I do. But when we talk satellites, for the Air Force, that means almost always one of two things. We fly satellites in space either to communicate or to take pictures of stuff. And for us, taking pictures is usually taking pictures of potential missile launches. Most of the satellites the Air Force flies are huge. And as an example on the left is a Boeing 702 product that they make. It's a communications satellite. And so the satellite is, well, how we're told that is, it's about 40 feet tall, 15 feet wide. These white things over here are people in white bunny suits. It's very, very large. And it's very, very large for a couple of reasons. First of all, it's a fair distance away from the Earth in geosynchronous orbit. It's actually 6 Earth radiuses away. I should have a diagram to show you what that looks like. The reason it's so far away is because if you back up that far, you can see half of the Earth at a time, which is awesome if you have something like the military applications where we want to talk to half of an Earth at a time. But if you're that far away, you need a lot of power and a lot of signal, and so they get very, very large. Also, we have, many people have a unlimited appetite for communications. And so it's actually just cheaper, at least it always has been in the past, just to build and fly the biggest satellite you can. It's not unlike, having the largest cargo ship that's practical. It's just cheaper to ship stuff in a big cargo ship than it is in a tiny boat. And so over the years, satellites have gotten this size for good reasons. That satellite, by the way, you're looking at maybe 300 million if you get a good deal each. Before you pay for launch costs, it's maybe 200-300 million for a satellite at that time. On the right-hand side is actually one of our satellites called Shark, and it's kind of on the other end of the spectrum. It's a small sat. It's something called a CubeSat, which I'll explain, and it's about 30 kilograms, much, much smaller. It can be smaller for a bunch of reasons. First of all, we're only doing one small thing with the satellite. There was a test of one thing. It was actually a communication test to transfer signals between, I think, essentially text messages between the ground, this satellite, and Globalstar, just kind of a cool test. And it's so close to the Earth that it actually can only see a small fraction of the Earth at a time. Now, it's surprising how small of a fraction of the Earth. If you go here in space, you can see not actually very, very, very much so. This satellite, if it was over Albuquerque, could also probably see like Santa Rosa and Grants, but that's it. It has to move over other regions. And so you need a lot of these satellites if you want to cover the entire Earth. But again, something of this size is sufficient for our experimental needs. And that satellite probably only cost us $5 million. I'll talk more about why it's that expensive here in a second. But for us, $5 million is a cheap satellite.
That's amazing. Hey, Matt, let's see, Ricardo has a question. Do you know what telecommunications, i.e. radio transceivers, go into a cube or a small sat?
I'm not an expert in that, but you have lots of choices. You can either, so the biggest challenge is getting permission to use the frequency. You can't just use any frequency you want to, well, unless you're a hobbyist. So you either use hobby frequencies or you use frequencies that have been allocated to the space people. And then you've got a set of transceivers and whatnot and antennas that go for those different frequencies. So that's the biggest challenge, is getting a frequency allocation. Because your satellite is going to be running through the broadcast of other people's satellites. And so you don't want conflicts there. And so that frequency allocation is really what sets what CubeSats end up using. Some people break the rules too, but we in the Air Force do not. We get the proper frequency allocation. We have a couple of what we call satellite integration facilities. This is the one that works on the smaller satellites. We work on satellites, you can see my hands, maybe the size of my outstretched arms, all the way down to these CubeSats. And this particular location focuses on those CubeSats. I'm going to stop sharing and try to jump back into.
Hey, Matt, I have a quick question for you.
Yes, ma'am.
So you know that giant satellite you showed us? So this is probably a very basic question, so don't laugh out loud. How do you get those up in space?
No, that's a great question. That's a very important question. That's the other reason satellites over time have gotten so large, is the way that since the 1950s, you get them up in space, is you buy one rocket and you put your one satellite on top of your one rocket and you launch it, right? It's very efficient. It's sort of an organizational dream, right? You just one rocket, one satellite. And so rockets are expensive to launch, whether it's a tiny rocket or a big one. There's tons of paperwork, there's tons of safety. And so over time, what you ended up doing was, since they're expensive, even if they're small, you build a big rocket and put a big satellite on it, right? That's kind of the dream. Again, it's the big cargo ship coming from China. sort of thing. It's the most efficient way to do it. The problem with that is what if you don't need a big satellite or a big rocket? You can think of putting multiple satellites on the rocket, but then you have to share. No one likes to share. That's an organizational challenge. And so it's become difficult. What I'll talk about in our small sat integration lab is the ultimate of that. And if you wanted to fly a really, really small satellite, what are you going to do? Buy a big rocket? So the rocket launches, a big rocket's $50 million. They do make small rockets now. They're about 5-ish. So that's a big deal to buy that. And so an entire industry has grown up in the small sat world about creating the satellites and the shape of the satellites, not because you want them to be a particular shape, but because they're easier to launch. And that's what I'll show you next. It's the economics of launching and how you get this in space ends up driving the entire way you build a satellite because it's so expensive to get them into space.
Thank you.
So you should see a first frame, I hope, of our small satellite integration lab. Did I do that right? Did I get a hallelujah?
I think you need to double click on it.
What I've been doing for 18 months and I still can't do right.
Got it. Small sat integration lab. Right?
Perfect. And any of you been in sort of a manufacturing facility, this is no different. It's a relatively clean environment. We have high bays, right? Sort of a multi-use environment for big or small satellites. I started with this frame because we actually have a lot of student interns over the year, and particularly during the summer, work with our team. That's another part of our mission that is part of my portfolio, really helping sometimes high school, but mostly university students, get excited about becoming space professionals. Not for my lab, we don't hire very many people, I wish we did, but for all the contractors and all the technologists around the country. So I want to show you sort of the creation of this Shark satellite. We'll talk a little bit about why it's shaped that way and how it's launched. So this is kind of the beginning of the satellite being assembled. And I tell the students, I remind them that the parts of the satellite are really no different than parts of your cell phone. There's antennas on the outside, there's electronics on the inside, there's a shell, there's cameras in it, there's sensors for acceleration, basically a phone, with a few other things as well. The reason ours costs so much, $5 million seems like a lot for what you're seeing in this picture, isn't because the parts are expensive. You might have $10,000 or $15,000 worth of parts. It's because at AFRL, we end up custom making every single one of them. They're all different to different experiments. And so it's the labor and the design work and all the testing work that eats our lunch. It eats everyone's lunch. That's why I mentioned that we're doing research and trying to have robots do some of this work. If you can get the robot to do most of the work itself, you don't have to spend too long programming it, then you could really potentially buy down the cost and increase the workmanship, frankly, of the finished product.
And let's see, Matt. Lenny had a question from Westwind. Is AFRL using 3D printing in the building process of the satellite components?
We are. We do have a research program in conjunction with UNM looking into how to best use 3D printing for the different parts. Most of the parts are space rated, if you will, right? Space is a harsh environment, and so traditional plastics, for example, won't work. But there is a growing understanding of what types of 3D printed processes will work best in space. And again, for us, replacing a machine part with a 3D printed part might be valuable, but what will be even better, right, is the customization and whatnot that comes from additive manufacturing and learning how to use that best. So yeah, that's something I'd like to talk more about. A couple more frames as this thing is being assembled. So on the outside these are patch antennas. These are these gray things. They're also called omnidirectional antennas. I think of an antenna being like your dish network antenna that's got some sort of parabolic to it. But these are meant to actually broadcast in most directions, right? So that when the satellite first turns on, in case it's not pointing the right way, it kind of spews energy everywhere to help us communicate with it. And then one of the other obvious differences between cell phones and satellites is that satellites, don't have USB-C ports. It'd be a very, very long cord. All of our current satellites in low Earth orbit, actually in Earth orbit, are solar powered. Bunch of different solar panels on here, a bunch of batteries inside to store the energy. Solar is a big deal. It's the lack of power is the killer for most satellites. So we try to cover as many as we can. In low Earth orbit as well, remember, these things are going to be in the dark half of the time. It's 90 minutes around-ish. 45 of those minutes are in the dark. We want it to still operate in the dark, so we've got to have enough battery power. A lot of earlier small satellites had deployable solar arrays, right? So you could make them bigger because they popped out. And we had many that never popped out, and it's a bad day when you put your satellite up there and it can't charge. That's a very, very short use of your $5 million or however much it costs. So I want to talk just briefly again, why is it shaped this way? Many of you know this. This is called a CubeSat, even though it's not a cube. CubeSat is a standard form factor. It's the shape of a satellite. When this gets in space, it could have been almost any shape, right? There's not very much air up there. It'll fly around almost any shape. But it's in this shape. It's basically 10 centimeters by 10 centimeters by 10 centimeters is a cube. This one is actually 6 cubes long. So it's a rectangle. And if you follow that form factor, it provides no advantage whatsoever, except for you can get it to space easier. And I want to show you how we do that. And so sort of the use of these CubeSats has really made the economics of doing small satellites, make sense. Otherwise, you'd have to buy your own rocket for this thing. And that wouldn't make any sense at all because you spend more on the rocket than you did on the satellite.
See, did you want to take a glance at a couple of the questions, or do you want to take a glance, or do you want me to read them to you? There's a couple long ones. I can read them to you.
Yeah, please.
Okay.
Yes, please.
From Sarah. Sarah is just amazing. About 30 years ago, I designed and manufactured an excimer laser micromachining workstation for AFRL Albuquerque for microelectronics manufacturing. Do you still have efforts to make your own microelectronics parts?
No, we don't do much of that work anymore. We have transitioned, we do some rad-hard electronics work, but we transition that mostly to using fabrication technologies that are common in the big factories, I believe.
Okay, terrific. Also, assuming I understand your earlier description, I'm curious what can be learned or shared with the manufacturing technologies, skill sets, or learning from the activities happening at AFRL UNM that could be developed for production, manufacturing, or industrial level manufacturing.
Yeah, I'd love to follow up on that. So that joint research effort in manufacturing of satellites started a couple of years ago, and an explicit point of that was to try to really be deliberate about transitioning the learning from that, the technology that comes out of that to industry. Because it doesn't help me at AFRL, right? If students know about it, right? That's great, but I need that knowledge to get to folks that work with us, right? Machinists, things that build stuff for us. So I'd love to follow up and see where we are with that UNM AFRL effort and see if that information is getting out to the community.
Okay, terrific. That's Scott Bryant from MEP.
So I mentioned these are all custom designed. We only ever do one, we see how it works, then we do something hopefully better and different. And so there's a lot of the cost of these things ends up being on the testing side. You're probably aware that we rarely as a country go up and fix any satellite. It costs so much to get them up there that it's usually not worth trying to bring them back and fix them or sending someone up to fix it. And so test is a huge portion of the cost of doing satellite work. That last one was us testing Shark satellite in an oven, essentially. You've got to test under cold and heat conditions, as well as vacuum conditions to make sure the thing is still going to operate in space. It's also a bad day when you figure out at this point that the design was wrong. You have to go back and redesign the whole thing because it won't survive in space. It's better to find that out now. And then here's what I mentioned about our trick. It's not ours. The trick people use to get CubeSats into space. So here they're loading that CubeSat, the 6-unit long CubeSat, into a dispenser. That's aluminum object here. It's made of aluminum. And what they do is they push that thing into that dispenser, and there's a spring at the bottom of the dispenser. You compress the spring and then close the lid. Then, as I'll show you, when you get up into orbit, you put the dispenser in orbit, and then you basically open the lid, and the spring pressure pushes that satellite out into space. Again, folks of a certain age may remember the Pez dispenser, right? It's no different really than a Pez dispenser, only the candy is actually the satellite. I was telling the fifth graders about the Pez dispenser, and I think in a class of 30, only like one had ever heard of a Pez dispenser. I'm like, oh no, I'm old. Another big cause of failures on satellites is vibration during launch. And so this is one of the vibration tables. It's basically a giant speaker that shakes. We program it to shake, not hopefully very similar to how the rocket shakes on launch. Again, we're trying to break it inside of its Pez dispenser before it gets into space, not after. It's kind of interesting to me too, just how to test some of these things better is also a research area of some interest. Doing researching on the test equipment for research satellites is sort of cool. Sometimes we test them alive, sometimes we test them when they're not on. And then just a couple more frames here when we're done with space. So what happens is our Pez dispenser, it's called actually a P-pod. I like Pez dispenser better, is actually in this frame being connected to 3 other Pez dispensers that have satellites in from other manufacturers. In this case, this company NanoRacks is actually on contract with NASA to provide this intermediary service, which I think is really cool as a business model. NanoRacks really is the intermediary between folks that have these P-pods and satellites and folks at NASA who will launch it. They put all of this together, and then this goes up on a cargo run to the NASA space station. And so here you can see those 4 now being packed inside of yet another case. The space community loves to put everything in cases and cases and cases. And this goes to the launch pad, and it was put on one of the Dragon capsules to go up to the space station. So when they put the space station resupply mission with lettuce, ballpoint pens, science equipment, these go up as well. What happens is the astronauts take this out, separate out their lettuce, and they actually place all of these Pez dispensers in 4 packs on the end of the robot arm. And that's what you can see here. These are actually a whole bunch of them. Then they aim the end of the robot arm in a safe direction, and they light fuse and get away. It's not a fireworks. They basically just open the door, and that spring pressure pushes our satellite out into space, and there's enough difference in velocity that this drifts safely away from the space station. And so the last frame I'll show is kind of grainy, but there's now 2 of these at a distance drifting away from the space station. So I think it's just fascinating to me, having worked in this field a long time, that it's really the economics of the space station and the intermediary and sending this stuff up in some standard form factor that makes this possible. We would have never been able to do this satellite experiment by buying our own rocket and building our own satellite. It just would have been too expensive to be practical. So I'm maybe obvious, I'm kind of interested in the economics of space and how that's going, because that's driving the technology really as much as anything. That's what I had on the space vehicle side of things, and we only have a couple minutes left. So I appreciate all of your patience for me blathering on, and would love to take any more questions about this or anything else we do at AFRL. Jack in the Box would be another good example. Thank you.
Tony, you have some thoughts, questions?
First of all, just thank you. This was really interesting. No immediate questions.
Sounds good. It really was wonderful, Matt. Thank you so much.
Well, again, I would love to invite you to come visit us when it's safe to do that again. It's a little bit more of a pain. It takes like a half a day to do what we just did in an hour. But I'd really love to show you some of the facilities, answer your questions, and it'd be a lot more fun as well if you could meet some of the folks that are actually working on this day by day.
Yeah,
Good question, Matt.
Yeah, it was fantastic.
This is Emily. Just wondering, do you do these regularly? Like, can we share in the future that you might be doing another virtual tour? This is so cool. I want to tell other people. And, you know, you mentioned doing it for kids. I mean, that seems something I'd love to share with, you know, other people in my life that have kids.
Yeah, please do. We don't have a regular time when we do these, but I end up doing this at least once a week. I have to take a nap afterwards because I'm an introvert, but so more than once a week. But I'd be really happy to do it, Emily, or anyone on here for once a week. Again, a class of 30 students works really well for this. It's a lot of fun. I'm just really happy to share a little bit. You know, even after we're able to take people onto base, I want to continue to do these because, you know, frankly, New Mexico is a very large state, right? If you're from Ruidoso or some other, you know, remote area, you're not probably coming to Albuquerque with your school group to see what we're up to. And to the extent that something like this has helped to inspire young people, and if we do it well, we want to keep doing this. So please give me your feedback and connect me to folks that might want to have a similar experience.
Sounds great. We have one more from Scott. Besides energy and brains, are there key New Mexican resources that are specific to your procurement?
Besides energy and brains. I'll have to think about that. Scott, I guess, can you help me with the question a little bit more?
Scott, are you still there? Scott Bryant?
Just quickly on, you know, procurement, we have a team in New Mexico that's doing research. And I should have mentioned, I do everything in halves. About half of our dollars that we collect, thank you, through the tax process to do this important work, stay in New Mexico. And we do work here, but about the other half goes, you know, around the country to all the places you'd expect space directed energy to be good, right? So we do a lot of our work contracted with, you know, big companies like Boeing, you know, small companies from around the country. And all of that very, very deliberate to both get the best technology, right, for our Air Force, but also to make sure that we just a bunch of different diverse ideas from around the country, right, come into our work. So not everything happens at Kirtland. Just all the cool stuff.
And like Scott said, this will be great for a tour or a virtual presentation is what I just added on. I guess it'll depend what's going on during manufacturing month in October.
Yeah, happy to do that.
Then he asked again, what kind of items might be specific to New Mexico minerals geolocation? Maybe was that related to his procurement question?
Yeah, I'm not, again, we have a huge history of space, particularly in some extent directed energy innovation in the state. That's one of the reasons we do the work here. That's kind of where I'm going with that question. The other reason we do the work here is, again, just the environment. We have large physical spaces. If you're propagating a laser beam, we do that on base sometimes for tests. We want it to go several miles. New Mexico is awesome because in that several miles on the base, you're not going to hit a tree. You're not going to hit a person. You're probably not going to hit a cloud either. Right. And so it's just a really great place to do testing of these sorts of technologies. I don't think the state gets enough credit for how valuable it is as just a really great test asset. So, well, again, thank you all for your attention. It's awesome. Your great questions. And I look forward to following up with many of you as I see you around.
Absolutely, Matt. Thank you so much for a great presentation. Thank you to Mary on our team for coordinating that with you. And we'll look forward to seeing you again. That was fascinating. I loved it. So everybody have a great day.